If you've ever tried to mix your own custom juice at a soda fountain, you already understand the foundational math behind computer graphics. When filling a cup, the physical rules are strict. If you want a drink that's heavily cherry with a splash of lime, you pour 75% cherry and 25% lime. These fractions must add up to exactly 100%, or your cup overflows. It turns out, when software programs combine two digital photographs, they have to follow this exact same physical logic. This digital process is known as image blending. It is a technique where we assign specific percentage weights to different pictures so they can share the exact same digital space. If we ignore the 100% rule and simply add the full light values together, the light overwhelms the pixel container. The resulting image turns into a solid block of overexposed white light. Let's look at how this works in practice. Suppose we have two completely different photographs, one of a dolphin leaping through the surf and another of a bicycle wheel. We want to combine them into one frame. The most intuitive approach is to just split the difference. We take half the light from the dolphin and half the light from the bicycle and add them together for a perfect 50-50 split. This is the resulting image showing that 50-50 average. Because both subjects share the exact same visual weight, they compete for your attention. The frame feels cluttered, and it's hard to tell what you're supposed to be focusing on. But what if we have a specific creative goal in mind? Let's say we want the dolphin to clearly be the main subject, and we want the bicycle to look like a faint, transparent ghost in the background. Simply averaging the two photos evenly won't get us there. We need a mechanical way to dial in the exact ratio of dominance between our two subjects. To do this, programmers use a digital slider called alpha. Alpha is just a variable, a specific mathematical percentage weight that we choose to assign to our primary image. Setting alpha to 0.75 gives the dolphin exactly 75% of the visual intensity. Thanks to our cup overflow rule, the second image's math resolves itself. The bicycle automatically receives the remainder from 1.0. 1.0 minus 0.75 leaves exactly 0.25, or 25%. Here is the photograph with that new 75 to 25 alpha split applied. The math does exactly what we asked. The dolphin is solid and clear, while the bicycle is pushed to the background as a faint, ghostly wheel. By forcing our two decimal weights to sum to exactly 1.0, the overall maximum brightness of the original images is perfectly preserved. The digital light doesn't overflow its pixel container. Now that we understand the concept visually, we can look at how a software engineer actually writes this set of rules. This code processes our blending logic. On line 3, image A multiplies by our alpha weight. Image B multiplies by 1 minus alpha for the remainder, adding them. On line 10, feeding the dolphin, bicycle, and a decimal weight processes the final image. When you look past the symbols and syntax, you can see the same physical rules we used with the liquids. This line of code is simply a set of instructions for a digital recipe. So the core mechanic always stays the same. You pick an alpha weight for your main image, and you give the exact remainder of 1.0 to your secondary image. This simple balancing act is the universal rule for combining digital media without corrupting the brightness of the final product. Let's put this into practice. Imagine a photo of a cat and a photo of a spaceship, and you want to blend them together into a single frame. If you want the cat to be the clear, dominant subject, with the spaceship barely visible in the background, what alpha ratio would you choose? Drop your numbers in the comments below. Digital visual effects rely on this precise balancing act. It is a matter of middle school math and a simple